In 73 seconds, 7 people will die.
Engines at 65%, 3 engines running normally, 3 good fuel cells, 3 good APUs. Engines throttling up, 3 engines now at 104%.
January 28, 1986, Florida. One of the most ambitious Space Shuttle Challenger took off. Just 73 seconds later, it mysteriously exploded and all 7 crew members were killed. After investigation, they found the culprit. It was this tiny devil, the O-ring. Such humongous missions are at the mercy of components smaller than your fingernail, the ones they couldn't afford to see fail. SpaceX has been planning a similar mission, a rocket designed to carry humans back to the moon, as the primary human landing system for NASA's Artemis missions. It will take astronauts from lunar orbit all the way to the moon's south pole. But before this mission, SpaceX will be testing a mammoth, something humanity has never witnessed before. It's the heaviest and most powerful flying object in human history. They call it SpaceX's Starship version 3. Think of it as a test drive for the vehicle that will eventually carry astronauts to the moon's surface. What will decide their fate are these 8 tiny components. On the 28th of January 1986, the morning was unusually cold. The freezing temperatures made the rubber O-ring lose its elasticity. It couldn't seal properly. Hot gases escaped, and within seconds, a chain reaction destroyed the entire spacecraft. SpaceX Starship version 3 will be using an O-ring too. At first glance, they look simple, just small circular loops, but their role decides if the mission survives or not. O-rings prevent any leakage of fluids or gases, especially in systems operating under extremely high pressure or cryogenic temperatures. These tiny components are used throughout a spacecraft, in valves, joints, and connection points. In a rocket, that means keeping fuel, oxidizers, and pressurized gases exactly where they belong. Their most critical job is to fix the illusion of perfection. When 2 metal parts are joined together, they may seem perfectly smooth, but in reality, there are always microscopic gaps between them. An O-ring or gasket is placed between these surfaces and compressed tightly. These are usually made from flexible materials like rubber or advanced polymers. In rocket systems, these are extremely crucial. Even the smallest leak of volatile substances like liquid hydrogen or liquid oxygen can lead to disaster. O-rings provide a compression that allows the material to deform slightly, filling in those tiny gaps and forming a secure, leak-proof seal. Space agencies say they've perfected use of O-rings. Incidents like these won't happen again. But can they assure that the tiny component behind this disaster is safe for future missions?
And Columbia, Houston, we see your tire pressure messages and we did not copy your last.
Roger.
There was nothing more. People on the ground saw the streak of the shuttle breaking up.
And then suddenly things started raining down out of the sky.
February 1st, 2003. Space Shuttle Colombia was returning from their mission. Astronauts were sent to low Earth orbit to perform scientific experiments. Everything went fine. On the mission's final day, the crew was just 16 minutes away from landing safely on Earth, but destiny had other plans. Columbia mysteriously ripped apart and its burning pieces scattered like fireballs across the horizon. It killed all 7 astronauts on board. Then speculation of the devil that killed them began. The disaster that killed them didn't begin during re-entry or during their mission. It began 16 days earlier, seconds after the space shuttle left the ground. The tiny component that doomed Columbia mission is smaller than your fingernail. It's similar to the one that decides Starship's fate during its re-entry. The moment Starship re-enters Earth's atmosphere, it faces the wrath of physics. It's moving at 25,000 kilometers per hour. That is almost 50 times faster than a Bugatti Chiron at top speed. But at that velocity, the air in front of the spacecraft compresses so violently that temperatures rise beyond 1,500 degrees Celsius. This isn't just heat. It's a combination of extreme thermal energy and aerodynamic stress, powerful enough to melt unprotected metal. To survive this, Starship has its tiny saviors, shield tiles. Starship is covered with roughly 18,000 silica-based heat shield tiles. These are designed to absorb, withstand, and dissipate that intense heat, protecting the structure underneath during re-entry. But this isn't the hero of this section. Each of those tiles is secured by tiny pins and clips, something that is almost invisible compared to the vehicle itself. These small mechanical fasteners hold the tiles firmly in place, even as the spacecraft experiences violent vibrations, rapid temperature changes, and structural expansion. But in Columbia's case, the disaster began at launch when a piece of foam struck the left wing. It damaged the heat shield. During re-entry, superheated gases entered through that breach, and that led to the catastrophe. But in Starship's case, many of these tile pins are installed with the help of autonomous robotic systems to ensure precision at scale. Past missions had one difference. In earlier programs like the NASA Space Shuttle program, heat shield tiles were attached using specialized adhesives, such as room temperature vulcanizing silicone. While effective, this method had limitations. Under repeated stress and thermal cycling, tiles could weaken or detach. Lifting Starship off the ground is difficult, but lifting it efficiently is an entirely different battle. So they use this, an engineering marvel barely wider than a human hair. Injector orifices are incredibly small, precisely machined holes and often less than 1 millimeter in diameter. They're located in the injector plate of rocket engines like the Raptor engine. They are microscopic, but their job isn't. They have one of the most critical tasks in the entire propulsion system: mixing fuel and oxidizer in exactly the right way for efficient combustion. Inside a rocket engine, fuel and oxidizer are stored separately and for good reason. They must only come together at the exact moment of combustion. That is where the injector plate comes in. It contains hundreds, sometimes thousands, of these tiny orifices. Each one is carefully designed to control how the fluids enter the combustion chamber. Then the magic happens. As liquid fuel and oxidizer are forced through these micro holes at extremely high pressure, they break into fine sprays, a process known as atomization. This allows the two substances to mix thoroughly and burn evenly. Without proper atomization, combustion becomes unstable, inefficient, and potentially dangerous. But they have a weird issue, the precision problem. The shape, size, and arrangement of these orifices must be absolutely perfect. If the holes are too large, the propellants won't mix properly. Too small, and the flow gets restricted. Engineers have to strike an exact balance to achieve stable combustion and maximum thrust. That decides how smoothly and powerfully a rocket engine runs. When that moment arrives, the happiest person will be Elon Musk. But for that, he has to pass the hair test. If you zoom into Starship and keep zooming in, you will notice micro joints inside steel tanks and pipes. These are incredibly tiny welds, sometimes thinner than a human hair. They don't control, start, stop, or regulate fluid flow, but hold together the systems carrying fuel, gases, and pressure throughout the spacecraft. Take a stainless steel propellant tank, for example. It might look solid from the outside, but it's a deceiving look. It's actually made from thin metal sheets joined together. So engineers don't just weld them in the usual sense. They use ultra-precise methods like laser welding or electron beam welding to fuse the metal at a microscopic level. A focused energy beam hits the joint. It melts a very small region, and as it cools, it forms a clean, strong bond without deforming the surrounding metal. The result? A seam that's incredibly narrow but strong enough to hold high-pressure fuel. But that's not a foolproof technique. To make it completely secure, scientists use a gas, not the one your friend who's on a high-protein diet, but the one nature has given us. Imagine a spacecraft carrying liquid fuel through tiny steel pipes. If even one microjoint develops a microscopic crack, fuel could slowly leak into space. At that moment, there's no way to fix it. That's why agencies like NASA and ISRO test these joints using methods like helium leak detection, where even the smallest escape of gas can be detected. But these joints have to handle the environment too. They must survive rocket launch vibrations, extreme temperature swings, and the vacuum of space, all while staying perfectly sealed. With these components, Starship has a successful liftoff, but after that, it's just an unguided missile. What will guide it are the spacecraft's synapses. Electrical connectors and solder points form the critical links between systems. These are tiny metallic connections, typically a few millimeters in pin size. Overall connector dimensions range from about 0.5 to 5 centimeters. It ties together avionics, sensors, and control systems, allowing signals to travel between the flight computer and every piece of hardware on board. They may look insignificant, but they carry essential commands like fire thruster, adjust orientation, or send data back to Earth. Inside a spacecraft, thousands of thin wires and circuit paths must be connected with absolute precision, the kind of accuracy where you see a fly in the toilet and aim at it exactly with the stream from your weapon. Engineers use soldering, melting a conductive metal alloy, to bond these connections at specific points on circuit boards and connectors. A magic happens when the solder cools. It forms a solid electrical path that allows current and signals to flow reliably. However, studies by NASA highlight that these interconnections are also among the most vulnerable parts of spacecraft systems. Failures can arise from bent or recessed pins, contamination that interrupts electrical contact, corrosion of connector surfaces, weak pin retention, or cracked crimp joints. Calculations for extreme environments are completely different. Risks like cryogenic failure, vibration damage during launch, and thermal cycling in space can degrade these connections over time. Even small workmanship errors such as miswiring, poor assembly, or handling damage can introduce faults that lead to intermittent signals or complete electrical failure. To prevent such failures, connectors undergo two weird tortures. First, they're exposed to random and sinusoidal vibration and shock, often up to 20 G. That too in 3 simultaneous directions for extended periods. This ensures that no misalignment or mismating occurs under launch conditions. The second case is a bit different. They're subjected to environmental tests, such as salt baths, to verify sealing integrity and resistance to corrosion, preventing particle ingress that could damage conductive surfaces. Think of it like this. A command from the flight computer must pass through multiple connectors and solder joints before reaching its destination. If even one connection fails, the signal may be delayed, corrupted, or lost entirely. These connectors act like synapses in the brain. They're tiny but essential links that keep the mission alive. During the mission, all we can hope is Starship doesn't turn into a fireball. I say this because it carries something weird. That is its biggest blessing, but a bigger curse than it. Rockets break free from Earth's gravity using enormous energy. It's driven by the combustion of cryogenic propellants like liquid hydrogen at -253 degrees Celsius and liquid oxygen at -183 degrees Celsius. These propellants are powerful, but they're also incredibly dangerous and delicate. In such an extreme environment, ordinary valves are completely useless, like trying to build a spacecraft window out of regular glass. To tackle this, they use something almost the size of your finger, cryogenic microvalves. These specialized aerospace cryogenic valves have become a core component of the fuel system. Within this system, microvalves are typically just 1 to 5 centimeters in size. They're small and often hidden, but they carry responsibilities far greater than their size suggests. Cryogenic microvalves operate in delicate and high-precision areas, auxiliary propellant lines, pressurization systems, and deep inside engine subsystems like pre-burners and cooling circuits. For Starship, it's a critical thing. Inside that mammoth compact header tanks, one for methane and one for oxygen, are used during the final descent. This is where these microvalves take over. They carefully control low-flow propellant delivery during landing burns and ensure stable engine relight in engines like the Raptor engine. It acts like ultra-fine regulators. They constantly adjust flow rates based on commands from onboard systems, where even the slightest imbalance in the fuel-to-oxidizer ratio can reduce efficiency or destabilize the engine entirely. But one risk related to it can fuel a chain reaction. These valves regulate pressure in smaller fluid lines. They support fine control systems like attitude thrusters and maintain stable operation under extreme conditions, cryogenic cold, intense pressure, and violent launch vibrations. If even one cryogenic microvalve fails, whether through leakage, blockage, or delayed response, it can disrupt the entire fluid system, and that can trigger a chain reaction that leads to engine instability and risk of mission failure. This precision leads to perfect exit from Earth, but to sustain the mission it needs something special: digital bloodhounds. Inside advanced rocket engines like the SpaceX Raptor, a tiny hero is constantly monitoring the real-time situation. What makes them truly powerful is their ability to capture extremely fast, dynamic pressure changes inside the engine. They could be as small as a grain of rice. They call it the piezoelectric pressure sensor. It is built using materials that rely on the piezoelectric effect. Basically, they convert pressure directly into electrical signals. According to engineering studies, these sensors have a very high sampling frequency, allowing engineers to closely analyze combustion behavior and engine dynamics in real time. It matters because that makes them the shadow prophet. Rocket engines need a stable, steady flame to operate efficiently, but in reality, combustion can become unstable. That creates pressure oscillations that reduce efficiency or even damage the engine. But piezoelectric sensors detect these instabilities early, helping engineers adjust fuel injection, improve combustion, and prevent failures. In fact, detailed sensor data has been used to identify the exact cause of engine issues and fix them quickly during testing. But if this tiny sensor fails, the consequences can be serious. Without accurate pressure feedback, the system can't detect combustion instability or pressure spikes. That could lead to inefficient burning, ignition failure, or even catastrophic engine damage. But a weird thing happens when the rocket rotates. Mini Antman is taking notes. This component is one of the most invisible components inside a rocket: MEM's gyroscopes. These are tiny sensors, just 2 to 10 times smaller than your fingernail. They're typically just 1 to 5 millimeters in size, yet they play a crucial role in helping a rocket understand its motion in space. They're built using microfabrication techniques similar to computer chips. MEM's gyroscopes contain microscopic mechanical structures engineered with extreme precision. Inside each sensor are tiny vibrating elements. When the rocket rotates, these structures experience something called the Coriolis effect. This effect causes a subtle change in the vibration pattern, depending on the speed and direction of rotation. The sensor detects these changes and converts them into electrical signals, which are then sent to the onboard computer. And this data is the rocket's sixth sense, because a rocket doesn't just need power, it needs awareness. It must constantly know its orientation, its rotation, and its trajectory to stay on course. MEM's gyroscopes provide that information in real time, feeding it into guidance systems that make instant corrections using thrusters or control mechanisms. Organizations like NASA and ISRO rely heavily on these sensors as part of their navigation systems. Without them, precise flight control simply wouldn't be possible. SpaceX Starship stretches to about nearly 400 feet, is 9 meters wide, and weighs around 6,000 metric tons. This is roughly the combined weight of 1,000 African elephants. They're powered by 39 advanced Raptor engines. It aims at over 89 meganewtons of thrust. Imagine 1,500 African elephants on a giant scale. Starship Flight 3 has enough raw power to push that entire stack of elephants into the sky at once. Back in the 80s and 90s, spacecraft like the Space Shuttle Challenger were considered absolutely massive. They stood about 184 feet tall and weighed around 2,040 metric tons fully fueled, with roughly 30 meganewtons of thrust at liftoff. That time, not just machines were small, but even the decisions were terrible. The Challenger disaster wasn't just a technical failure, it was a decision failure. According to reports, engineers had already warned that O-rings could fail in cold weather, but the launch went ahead anyway. In that era, O-rings used in the solid rocket boosters were extremely large, about 6 meters in diameter with a cross-section of roughly 7 to 8 millimeters, and served as critical structural gas seals. In contrast, modern spacecraft use much smaller O-rings, typically in the millimeter to centimeter size range. It is primarily for fluid system sealing in valves, pipelines, and engine subsystems, where conditions are more controlled. These are supported by multiple redundant seals, advanced materials, and strict inspection protocols, including repeated checks during flight testing and before launch. Certifications like AS9100 ensure that O-rings meet the highest levels of safety, reliability, and consistency required for aerospace applications. What happened in the Space Shuttle Challenger disaster has not been allowed to repeat. The major reason was engineers moved away from relying on large, single-point failure O-rings in structural gas seals. Since then, organizations like NASA and SpaceX have placed enormous emphasis on the design, testing, and redundancy of seal rings and gaskets. The Space Shuttle Colombia disaster was a tragic remainder. On February 1st, 2003, Space Shuttle Colombia broke apart, killing these 7 members. But a similar kind of mission was carried out a few days earlier, Artemis II. Out of all the reasons behind its success, the least discussed were these micro-components it was at mercy of.